So our next talk is going to be on the very important topic of how to do general purpose parsing. Michael Adams is going to be giving the talk, and Michael is going to be on the academic job market this coming season. This is work that he's done with Celeste Hollenbeck and Matthew Mike.
Thank you. Is this good enough for everyone? Okay, cool. So as was said, this is joint work with both Celeste Hollenbeck and Matthew Mike. And if you take away only one thing from this entire presentation, I want it to be this. Parsing with derivatives has been around for about half a decade, but has been notoriously slow. So slow it's impractical to use. However, with the paper we are presenting today, we can demonstrate that parsing with derivatives can not only be implemented quickly or implemented efficiently, but also it's not too hard to do if you know the right parts to tweak. Since this is a presentation about parsing, I do have to address the question of, isn't parsing a solved problem already? We have so many different techniques, from GLR, LR, LL, different implementations, Parsec, YAC, etc. Why do we need another parsing technique? Well, it may be the case that parsing is solved in some domains, but parsing is a problem that we see in many other domains as well. For example, if you're writing a network server, the protocol that you're talking over is often specified in terms of a grammar and some RFC. But if you look at these in the wild, you will often see that these implementations don't use a parser. Instead, well, they don't use a parser framework. Instead, they implement it by hand. So, for example, Apache uses about 2,000 lines of handwritten C in order to parse HTTP. Similar results, they're about 1,000 lines for light HTTP. Courier for IMAP and Freenode for IRC are about 2,000 lines of handwritten, buggy, potentially security vulnerable code. And because of this, we get things like heartbleed and shell shock. Those were both examples where an input was not properly parsed and validated, and this led to vulnerabilities down the road. Okay, so we've got parsing frameworks such as YAC. Another way we see in the wild is pointer bumping. Pointer bumping. Another place we see this problem is in configuration files. If you look in your /etc directory, you'll notice very quickly that these files were not designed to be parsed by something like YAC. They were designed to be parsed with something like strtalk. Now, there are many reasons why parsing frameworks are not being used in the wild. But one of them is certainly that using YAC is a pretty high overhead. In order to use the YAC, you've got to write your .y file. You have to define half a dozen data types, tell YAC about them, write your rules. You finally can compile the YAC rules, and it hands back to you 100 or maybe a couple hundred shift-reduce conflicts or reduce conflicts. You have to go off and debug them, and then there's always the one that you can never figure out where it's coming from. You just hope that that works. And I'm only halfway through that list. On the other hand, if I'm using buffer pointer bumping, I couldn't get that right one day. Pointer bumping or strtalk, I just do the parsing work directly and move on and work in my program. And furthermore, I don't even have to leave the language I'm in. I'm programming in whatever language I'm using. Enter parsing with derivatives. The original Parsing with Derivatives paper showed a way of writing a general-purpose context-free grammar in only about 100 lines of code, depending on how much you're doing. Hopefully, this is simple enough and small enough that you don't have to think about going off to find some library to do it. You can just implement it yourself, and then if later on you need something more high performance, you can transition over. But you get a very cheap way of doing parsing quickly and easily. Of course, there was one Now, the way parsing with derivatives works is we have this concept of a derivative of a language, and this is borrowed from Zasowski in 1964. And the derivative of a language L relative to a character C is the set of strings such that when any of those strings is prefixed by C, we get a language in L. So for example, let's suppose L is the language foo bar frac. and we want to take the derivative of L with respect to F. What we do is first we have to eliminate all of the strings that do not start with F. So bar goes away. Then we remove the initial F from any of the remaining strings. So we are left with oo and rack. Now we can take another derivative of this language. This time we're going to take the derivative by O, which leaves behind only the string O. We're going to take one final derivative with regard to O again, which means our resulting language has only epsilon. Now this epsilon is important because it tells us that the sequence of characters by which we took the derivative, if they were concatenated together, would have formed a string in the original language. So in this case, this is telling us that FOO is in the language L. Now, operating over sets is not necessarily what you want to do if you want to encode this on a computer, because some of these sets are infinite. But you can come up with a set of equations that determine how the derivative operator works on typical grammatical forms. For example, concatenation, choice between alternatives, tokens, etc. Each of these rewrites is pretty straightforward, and in turn can be pretty straightforward and can be converted into code with the pattern matching on its input and producing the output. Now you have to do this for 2 or 3 functions, but at the end you have a short implementation with a fully general parser that fits on a single slide. Problem, however, is a question of performance. The original Parsing with Derivatives paper, when they took a look, when they computed the asymptotic complexity, they came up with a result that's exponential. It's actually to the 2n exponential. Furthermore, this wasn't just a theoretical problem. They reported taking 3 minutes to parse 31 lines of Python. Now later in the paper, they introduced an optimization that they call compaction, which reduces that down to 2 seconds. But 2 seconds is still really slow for only 31 lines of Python. To give you a sense of scale for this, we ran, in the current paper, we ran some benchmarks and found Parsing with derivatives to be 24,000 times slower than Python. So, the current paper attempts to address both of these problems. First, we show that Parsing with derivatives is actually cubic. It wasn't exponential, and that's the original Parsing with derivatives, with or without the compaction step. Second, we look into how we can implement Parsing with derivatives more efficiently. So we were able to take it down to 25 times slower than Python instead of 24,000 times. So let's take a look at this first result on complexity. Here, this is the derivative code that we saw very briefly before. This is taking the derivative of the language L with respect to the character C. Now, you don't need to read all of this. There's just one case in here that's important we want to pay attention to. And in this case, we are matching that L is equal to a sequencing or concatenation between 2 other languages, L1 and L2. In this case, we end up generating 2 different possibilities. So, to parse, if we take the derivative of L, we either need to consume a token from L1 and then concatenate the result with L2. So this is, we've got a sequencing, we're looking at L1, we want to consume a token from that there. And that's what the left-hand branch of the alt node is doing. On the other hand, since one of the side conditions for this case is that L1 is nullable, which means it contains the empty string, we could skip over L1 and directly proceed to parsing within L2. And so that's the right-hand side of the alternative node. Now, in the original Parsing with Derivatives paper, they observed that this leads to a duplication of L2. And the concern was that we might be able to trigger a chain of these duplications, which would cause an exponential behavior. However, parsing with derivatives requires that the derivative function be memorized. So some of the calls onto L or L2, they might actually be free. Now, this gets a little complicated to account for if we think in terms of trees that are duplicated. However, we can come up with an accurate bound on this if instead of thinking of the trees that are duplicated, we think in terms of individual constructors that are being constructed. This is because when a new object, when a new constructor is being called to construct an object, there might need to be a new entry in the memoization table for that constructor. So, if we can bound the runtime by the number of tokens that are allocated as we go throughout the language. Now, in order to count how many of these there are, we're going to give each node a unique name. We're going to come up with a naming scheme for that. Then we're going to show that the number of possible such names is n cubed. So the naming system we're going to go with is, we're initially going to start with every node in a grammar, which is going to have its own unique name. So the grammar L here on the left is being given the name L on the right. Then when we take a derivative of a language, we take the character by which we're taking the derivative and concatenate it onto the name of the node. So if we take the derivative with regard to F of the grammar L, we get LF. And we can keep on going, taking the derivative successfully, until eventually we have a node with the name FOO. Now, one of the nice things about this naming scheme is that the characters that are being concatenated to that initial name are always going to form a contiguous subsequence of the input. This means that the possible number of characters, or the possible sets of characters that could be appended is quadratic, because there's in places in the input string it could start and in places in the input string it could end. There is one problem, however, and that is this case that we looked at before. Because what's happening here is that on the left-hand side, we have the sequence node named L, but we have not just one, but two nodes being constructed on the right. And if we named both of them LC, well, our names are no longer unique, so our previous argument is going to be undercounting the number of possible nodes. We could rectify this by changing the naming scheme just slightly. In front of the C, we're going to insert a little bullet symbol. This is going to be a special character that's distinguished from all of the others, and this will ensure that the names for all in sequence are different. However, there's also an important trick being played here, because by naming it in this way, we guarantee that a bullet can be placed in a name, can occur in a name at most once. This is because if you have a grammar node and you want to you want to add a bullet to it, then that grammar node that you start with has to be a sequence. However, the only names that already have a bullet in them, those are either alt nodes constructed by this rule or some derivative of that alt node, which will also be an alt. So once you get a name into a grammar label, once you get a bullet into a grammar label, you know that grammar node is an alt. And that grammar node can never trigger this rule again, so you're never able to put another bullet in it. So this allows us to revise our previous analysis. There are now two types of names that could occur. First, you might have no bullet in the name, just as we had before. But now there's a bullet that can occur. At most one of them occurs, and so that adds just a linear extra factor. This gives us the n-cubed result that we were looking for. And this is good, because most parsing algorithms fall into this category, complexity-wise. However, there's still a bit of a performance problem. So in order to take a look at this, we went to the parsing with derivatives code, and our plan was that we were going to benchmark it, find a few hotspots marked here in red and yellow, and then work on that, try to optimize it, so we got an efficient implementation. However, what actually happened is once we looked at the parsing with derivatives code, and we profiled it, there wasn't one single hotspot that we could target. The inefficiency was just sort of spread throughout all of the code. So we had to scrap that idea and come at it from a different approach. And that is that we started from a clean slate, empty file, and we implemented a small fragment of the parsing with derivatives code. We benchmarked that and profiled that fragment of the implementation, and if some part of it didn't perform as well as we would have liked, right then and there, we went through and tried to improve its performance. Then we would add small fragments of the implementation on and benchmark and profile and optimize each of them as we went along to finally produce fast and efficient implementation. Now, in doing so, we found several optimizations that have done allow us to get a more efficient implementation. They fall into three general categories. One has to do with compaction, which is the algorithm I mentioned before that Mike et al. Used to take parsing from 3 minutes down to 2 seconds. We found some improvements on that algorithm. The other has to do with how the nullability of the function is being done. Previously, it was being done with an iterative fixed point. We moved that to being done as a dependency graph. And finally, and this is one of the more interesting ones, I think, but it's a little bit intricate for a talk here, for constraints of the talk, rather, was dealing with the memoization table. Memoization table, you think, oh, that's going to make it go faster. But we found that the lookup into the memoization table was taking enough time that it slowed the whole thing down. Now, as I mentioned before, I'm not going to go through all of these, but I want to show you one example of an optimization that we found. It could happen that in your grammar, you end up with a chain of concatenations, balance down going to the left. This might occur in your original grammar, or it can actually occur quite easily in one of the intermediate grammars as you're taking a derivative. So, for example, if you've got some nested parentheses, and the parser has consumed all of the left parentheses, well, what you're left with is this chain that is the middle that's going to be appearing as this left-hand branch. Now, the problem with this is that as you're taking the derivative of this grammar, you want to try to consume tokens out of L1. Well, to get to L1, you're going to be hitting every single one of those sequence nodes. Then you're going to go back up, and you take the next derivative by the next character. You're going to hit every one of them again. It would be far better if instead of being balanced to the left, we make it balanced to the right. Then, in order to consume a token out of L1, we only have to hit the one sequence. Now in the paper, we have lots of graphs demonstrating the effect and the reasons we chose each implementation. But here is the graph you actually care about. The short version of which is we were able to make parsing with derivatives be fast. We were able to take parsing with derivatives from being 24,000 times slower than parsing to being only 25 times slower than parsing. And the implementation isn't all that much more complicated. We moved from 130 lines of racket to 180 lines of racket. Still, it requires a little bit more effort and work, but still easily within the realm of possibility for your average program. So, to summarize, the computational complexity of parsing with derivatives, it turns out, is not exponential. We can show that it is cubic. Furthermore, the slow implementation of parsing with derivatives is not something we have to put up with. We can improve its performance by 3 orders of magnitude. If you're interested in playing around with this implementation, we have that online, so you can play around and experiment with it and try it in other languages or in your own systems. And now I would be happy to take any questions.
Just a very simple question, but what is n?
N, the question was, what is N?
Is this the input? Like
It is the
grammar size
length.
or-
It's the length of the input.
Of the input?
Yes.
Okay. Okay. So, okay.
Another small question. Can we go back to the graph?
Yes.
I couldn't read the bars in the back.
With this graph?
Yeah, you showed up top, there was old parsing with derivatives.
Yep.
And then down below is new parsing with derivatives. Does each horizontal line correspond to a different parser?
Okay, so the way this graph is working is it is plotting in the horizontal axis the number of tokens in the input. So we took all of the Python standard library and parsed those files, and we timed for each file. In the vertical axis is the normalized time to parse one token. So in this case, down is better. Note that the vertical axis here is logarithmic. So we are dealing with the old parsing with derivatives would take a tenth of a second for most of those files.
These dots are all different. What are the dots?
Yes, okay, so there's 4 clusterings here. The top one is the old parsing with derivatives. The second from the top is Racket's built-in parsing tool /CFG. The third from the top is our new improved parsing with derivatives. And the bottom one is Bison.
Okay, thank you.
So I think this is really cool. I really like it. I had a question. When you compare it against Bison, Bison is, I think, LALR.
We were running it in GLR mode.
Okay, so it's general. And does the performance of derivative parsing depend on the class of grammar that's parsing? Or?
Well, if you think back to the example of moving the sequences from left to right, there are going to be artifacts in your grammar that could either improve or worsen the performance.
That's independent of class, right?
Yes, although some classes might exclude some of those possibilities. So you can't do a left recursion in LL, for example. We do not have benchmarks specifically addressing that question, so the answer is I don't know.
Thanks.
Hey, great talk. Thank you very much. I was just wondering how this, so you have a lot of comparisons to Bison. I was just kind of curious, how would this compare to, say, a parser combinator library like Parsing?
Okay. So the answer is still, I don't know. No, I really don't know, because there's actually multiple variables in play there. So parsec is written in Haskell. What we wrote is written in Racket.
Say instead of performance, just like the actual code itself.
Oh, the length of the code?
Yeah.
Implementing this in Haskell should be fairly straightforward. You could probably transliterate the code. And actually, I have done the transliteration of this code too. Is that right? Yeah. Transliterated it to a camel, and that wasn't too difficult. The one catch you might have to worry about is I don't know how the laziness in Haskell is going to interact with this. But it should transliterate to about the same size of the code, I'm estimating.
Thank you very much.
Also, usually when we are like designing a language, we make sure that we are going to get a linear time parser, and that's one of the reasons that people are using Python. I'm making that I'm consuming a character. And according to your results, if I'm interpreting it correctly, is it running a linear time most of the time, or like in your examples? Although the cubic is like the worst case.
So the grammar that this is plotting is the Python grammar directly taken from the spec, and just in the spec it contains stars and pluses, so we have to shred that so that Python doesn't know how to deal with cleaning star, for example. So we have to convert that into a grammatical form. That's a very naive translation that we're doing. And the Python grammar is designed to be, I think, LL parsable. Because both parsing with derivatives and when Python is running in GLR mode, it will do any. We didn't spend much time figuring out about what complexity flies. And I forgot the question.
Yeah.
What was the question?
The question was essentially, practically, your algorithm also looks like it's working like down.
Oh, linear, yes. Yes. So, yes, from this graph, it looks like on a typical implementation, it will go linear. We didn't really run into very many cases at all where it exploded off that. So for most languages, we suspect it's linear.
Thank you. It sounds really cool.
So the performance looks great, but you're saying it's still slower than Bison, but you claimed that it's easier to use than Bison. Do you have experimental evidence or clear evidence that this is easier?
Well, we've not run a user study, but one of the reasons that this would be easier to use in Python is that this library is something you directly call from your host language. You don't need a separate file that needs to be compiled and checked for errors or whatever. You never leave your host language. In fact, you can do fancy things that you couldn't even do in Bison, where at one time you generate your grammar and then hand it off to the parser.
Okay, thank you.
So, I'm not sure if I followed it exactly, but are you not memoizing the constructors, you're just memoizing the terms in the constructors? Or?
So we are, within parsing with derivatives, we are memoizing within the derivative function, we are memoizing on both arguments. So the input grammar and the character by which we're taking the derivative. And the result of that memo table is the grammar that comes back out.
I see, okay, thanks.
All right, unfortunately, we still have time. I'd like to ask the question. So I'll be teaching compilers in the fall.
Yes.
And so I'm getting that there's a library
There
that is
is
involved. And then you're also writing the parser for you're specializing the parser for your particular grammar.
Not quite.
Okay.
We have both the parser, which is the library that's involved, and
A parser for a particular language or a general purpose?
A general purpose.
General purpose,
parser.
okay.
Then you also have the grammar specific to your language. You or your students would have to be writing that grammar. And either you could use our existing implementation as a library to just use it, or you could assign your students the task of writing that 130 lines of code, so they implement their own parser from scratch.
I see. Okay, and you guys said it's 130 lines of code for the whole Python grammar? No,
No,
that was
that's
just
for the
the general
library.
purpose.
That's
That's
for
for
the
the library.
general
That's for the library. Okay. Have you used it in?
I've used it 3
Compile-
times now.
You've used it 3 times in compilers?
Yeah.
Okay, I'll be contacting you. Do you have any other questions? Yes.
Just a quick comment. I implemented it at least in part for parsing structure grammars, and it's actually pretty straightforward. So it's kind of work I've done. So it's not like if you look at the rules and like they're natural, there's a natural translation. That's why it's awesome, because implementing the derivative function is not like this nightmare. Like you can go look at it and it's.
So it's relatively straightforward. Any chance you did that in Haskell?
What's that?
Haskell? Did you do it in Haskell?
I think we did. I think there's a couple of implementations. I think one of them might have been in Haskell. But like if you just look at the rules, like
Okay.
they come out pretty straightforward. Enough even for students to look at it.
There's an old Haskell implementation for the original paper.
There's an old Haskell. Great. Fantastic.
Oh, I skipped over it.
Unless there's any more comments, let's thank our speaker again.